So far in this chapter, we've talked about concentration and stoichiometry and some different reactions that involve aqueous solutions, things that are dissolved in water. So we've talked about precipitation reactions that result in a solid precipitating out. We've talked about acid and base reactions that result in neutralization, where you get water out of it. The last type of reaction we're going to talk about now is an oxidation reduction reaction, or a redox reaction. And this is where oxidation states change. And I know that that really doesn't make any sense at this point, but really every single reaction is actually an oxidation reduction reaction. It just, depending on what happens, it looks a little bit different. So redox reactions by definition are reactions in which one or more electrons are transferred. So usually we think about reactions as making and breaking bonds, but in the case of redox reactions, we're actually transferring electrons from one species to another species. So the first thing we're going to learn about here is how to determine oxidation states. These are, and I can't stress this enough, imaginary charges. Remember when we talked about the difference between ionic and covalent bonds? Ionic compounds transfer electrons. They have charges because those electrons have left one species and has gone to the other species. But when we talk about covalent compounds, we talk about the sharing of electrons. Well, in oxidation and reduction reactions, we're actually going to assign charges to those covalently bonded molecules. That's because these charges are completely imaginary, and all it does is it allows us to do accounting. It allows us to keep track of where the electrons are, where they've been, and how they're behaving. So they're imaginary charges that the atoms would have if the shared electrons were divided equally between identical atoms bonded to each other. Or, for different atoms, we're all assigned to an atom in each bond that has greater attraction for electrons. Now this seems a little odd, but there is a whole set of rules that only applies, that only applies to oxidation states. And here are the rules. I know, something more for you to memorize. These aren't so bad though. An atom that's an element is always zero. So for instance, if you have silver by itself, its oxidation state is zero. Why? Because it can't have any more electrons or any less electrons than it already had, because its oxidation state is zero. We have O2. O2 is an atom that's an element. I know it's diatomic, but remember that that's okay. It's still only one element. When it's only one element, its oxidation state is zero. So those are the types of things that they're talking about. You're either going to see diatomics where the oxidation state is zero, or you're going to see metals that stand alone, its oxidation state is zero. Monatomic ions are the same as their charges. So what if we have Na plus in a reaction? If we have Na plus 1 in a reaction, it's already telling us its oxidation state. Whatever its charge is its oxidation state. What if we have Cl minus? Whatever its charge is its oxidation state. So far, so good. Now, some specific examples. Fluorine is -1 in its compounds. You know, you might as well say that all halogens are -1 because, for the most part, they follow that rule. But only when they're in the compounds. If, for instance, they're Cl2, now we're back to a monatomic ion, so its oxidation state is zero. Oxygen is almost always -2 in its compounds, and for the most part, it applies to the whole family. Not that you see a lot of sulfur or anything like that bonded to things, but oxygen is almost always -2. And hydrogen, we always consider it +1 in its covalent compounds. If it's an ionic compound, that can change, but it's almost always +1 no matter what. Now, I just went through those really quickly, and you're probably sitting there going, what? I don't get this at all. The easiest way to learn this is to start with an example. So let's assign some oxidation states. We'll zoom in here on CO2. So if we go back to the rules, we know that there is no set rule for carbon. So you can look all you want at your periodic table. You can assume that it's +4, but you really don't know until you do the math. The rule that we do have applies to oxygen. Oxygen is always a -2. So if its oxidation state is a -2, and there's 2 of them, that means we have 4 negatives. If we have 4 negatives, that means we have to have 4 positives, and so carbon has an oxidation state of +4. Please don't say it has a charge of +4. It really doesn't. A charge is a real thing. A charge is when electrons are physically attached to an atom and changes the charge of the atom. Oxidation states are imaginary. So there's a real difference between the two of them. I know this looks like just when we were doing nomenclature and we were figuring out charges of atoms in molecules. I know it looks the same, but it really isn't. All right, then let's go down to SF6. One of the rules says that F is always -1. There's 6 of them, so it's -6. That puts sulfur at a +6. It's an oxidation state. It's imaginary. It's not a charge. So it's okay for sulfur to be +6, even though when it's in an ionic compound, it's a -2. This is not an ionic compound. It's not a metal and a nonmetal. So we can assign this oxidation state of +6 to it, even though it may not make sense to us. That's why it's called an imaginary number. Sorry, it's not an imaginary number because it doesn't have an I in it, but it's imaginary because it's something that we made up. Now, these get a little more complicated. You'll notice here that this has a charge of a -1. That means that we need all of our oxidation states to equal a -1. Now we know that oxygen is a -2. That gives us a -6. So instead of making nitrogen +6 to give us a 0 charge, we're going to leave it at +5 because we want a -1 charge on the ion. So its oxidation state is +5. That gives us a charge of -1 on the ion. All right, let's go down and do some more vocabulary then. We have some vocabulary that you're going to become familiar with. You need to become familiar with. The first is reduction. Excuse me. That is a decrease in oxidation state. It's a gain of electrons. If you are gaining electrons, you are becoming more negative. Well, you aren't. The species is becoming more negative. So keep that in mind. You're looking for an increase in negativity if you're looking for reduction. Oxidation is an increase in oxidation state, which is a loss of electrons. And if you're losing a negative particle, you are becoming positive. You're not. The species is. But you get the idea. So, some mnemonics to remember this. Oil rig. Oxidation is loss, reduction is gain. Of course, they're speaking in terms of electrons, not in terms of charge, but in terms of, or oxidation state. They're talking in terms of electrons. An oxidizing agent is an electron acceptor. A reducing agent is an electron donor. I've always found the easiest way to remember this is the oxidizing agent is being reduced. And the reducing agent, I don't know why there's that space there, is being oxidized. So that makes it a lot easier to identify the roles of those two species. So here's an example, and we can read through all of this. You have powdered aluminum, it's doing all this stuff. The mixture bursts into flame, we get some purple smoke out. The equation for the reaction is that. So what they want us to do is identify the atoms that are oxidized and the ones that are reduced. In order to do that, you need to assign oxidation states. Now aluminum's pretty easy. It follows rule 1. It's an atom by itself. Its oxidation state is 0. Iodine, also an element by itself. Its oxidation state is 0. But now when we go over to aluminum iodide, there's no rule that talks about aluminum or iodine. But because iodine's a halogen, we can assume that its oxidation state is -1, which gives us -3 and makes aluminum a +3. So if we talk about oil rig, oxidation is loss of electrons. In other words, it's becoming more positive. Which one is becoming more positive? The aluminum. It's going from a 0 to a +3. Reduction is gain of electrons. That means it's becoming more negative. So which one's becoming more negative? Iodine. It's going from 0 to a -1. So another example, some more metallurgy. You can read all about it if you really want to. It talks about galena and how they get the ore out and all that other good stuff. It says for each reaction, identify the atoms that are oxidized and reduced, and then tell us which is the oxidizing and reducing agent. So again, we have to go through and assign oxidation states. Oxygen is where my eye goes first because it's an element. Oxidation state is 0. Now PBS is another one of those. We don't have it on the rules, so we have to assume because it's ionic that we can use the charge of the sulfur, which is -2, to figure out that Pb is +2. We go to the other side. We know that oxygen is always a -2 in both of those species. In PbO, again, it becomes a +2. In SO2, the sulfur becomes a +4. So if we write these all out, Pb stays the same, goes from +2 to +2. That means there has to be one that's being oxidized and one that's being reduced. O is going from a 0 to a -2. S is going from a -2 to a +4. Whenever you have oxidation, you have to have reduction. There's no such thing as one without the other. So now let's take a look at this. Oil, oxidation is loss of electrons. That because it means it's becoming more positive. That's our sulfur. Rig, reduction is gain of electrons. It's becoming more negative. That's the oxygen. And then which one's the oxidizing agent? The one that's being reduced. Which one's the reducing agent? The one being oxidized. Go down and do the next one. Oxygen's always -2. That makes carbon +2, Pb +2. Here, lead is by itself. You'll notice that oxygen's not staying, but Pb is going from +2 to 0. Carbon's going from +2 to +4. Oxidation is loss of electrons. Which one's becoming more positive? That's the carbon. Which one? Rig. Reduction is gain of electrons, becoming more negative. That's the lead. Which one's the oxidizing agent? The one being reduced. Which one's the oxidizing agent? Or, I'm sorry, the reducing agent, the one being oxidized. And now you have them all identified. All right, so it's a little different. All it takes is a little bit of practice. It's not overly difficult, but we will apply this then in 410 when we talk about how to balance equations that are oxidation-reduction reactions.